So we're going to continue talking about redox reactions and what happens when electrons are transferred in the reactions. Now we have a method of keeping track of the electrons. The method of keeping track of them are our oxidation numbers. So oxidation of metals by acids and salts, acids or salts, either one, usually take this format. So go ahead and copy this down. This is the format. You start with a solid metal, I'm calling that A, it's generic. You're going to mix it with an acid or a salt, so this is something that's aqueous, whether it's the acid or the salt. And then they're going to react, and you will get a new salt and a new solid metal. And what happens is this metal over here has an oxidation number of 0. In this case, the acid or the salt, these have oxidation numbers of plus and minus. This metal is going to lose an electron. It's going to lose an electron to this. And when that happens, it will then have a positive charge. And this thing will have gained an electron and now have an oxidation number of 0. This will make more sense when I do it with real things. But the reason I wrote it like this was because an oxidation reduction involves electrons, this little guy, being transferred. So take a second and copy this equation. Here we have solid zinc metal combining with hydrobromic acid to make zinc bromide plus hydrogen gas. Take a second, pause the video, copy it. And now that you're back, look closely at this format. You know this format as something called a single replacement reaction. Now we're giving it another name. We're saying this single replacement reaction is also a redox reaction because as part of this single replacement reaction, the zinc replacing the hydrogen, electrons are being transferred. Now let's look at how we would figure that out. This zinc is an element, zinc, in its elemental form. It's a solid metal. So anything in its elemental form has an oxidation number of 0. Now let's look at the hydrogen bromide. Hydrogen usually has a charge of +1, especially when it's combined with nonmetals, and bromine is a nonmetal. Bromine is a halogen, and we said in our rules that halogens are usually -1, and in this case that's going to be -1, which makes +1 plus -1 gives you an overall charge for this compound of 0. Let's see what happens on this side. Over here, I'll keep it in black. Bromine is still usually -1, so we're going to assume it's -1, and we have 2 bromines here. So that means we have an overall charge here of -2. Which means if this overall charge for this bromine, and I'm taking -1 for each bromine, but there are 2 of them, that's how I get the -2. If the total charge on the bromine is -2, then the total charge on the zinc has to be +2. Hydrogen gas over here, the hydrogen in its gaseous form is in its elemental form. It's not an ion, so this is going to have an oxidation number of 0. So let's look at what happened. Zinc went from having an oxidation or a hypothetical charge of 0 to having a hypothetical charge of +2. So zinc, in order for that to happen, zinc had to lose 2 electrons to get a positive charge. On the flip side, hydrogen went from having a charge of +1. So this hydrogen went from having a charge of +1 over here to 0. Now this is where it gets a little tricky. This hydrogen has a charge of +1, and here it's 0, but there are 2 hydrogens. 2 hydrogens, they each have a charge of +1. So the hydrogen itself, each one went from +1 to 0, but since there are 2 of them, they each gained 1 electron, or together they gained 2 electrons. They gained 2 electrons together, or separately they each gained 1. So this is your molecular equation. I'm going to circle it in purple. You don't need the numbers. Once you have it figured out, this is your molecular equation. It is actually the single replacement reaction is your molecular equation. But now we're going to write the net ionic equation. What changed? I'm going to need more space. Okay, so in a net ionic equation, any net equation, let's call it just a net equation, we only write what changed. We only write what changed. And I want to say something else that you should write down. In order to have a redox reaction, we have to have something reduced and something oxidized. You can't have one half. So let's look at our equation up here. What was reduced? Well, oil rig, oxidation is losing, reduction is gaining. What gained electrons? Our hydrogen gained electrons. So if it gained electrons, it's the one that was R, reduced. So hydrogen was reduced. I'm going to write that under the word reduced. So we figured out which one was reduced. And the way I think about reduction is it's a reduction in positive charge. So the positive charge here went from +1 to 0. It was reduced. It's another way to look at it. Which one was oxidized? Well, oil, oxidation is losing. The zinc lost electrons. So the oxidized element was the zinc. Zinc was oxidized. You can't have reduction without oxidation. They have to happen together because electrons are being transferred. They can't get one key. If something loses an electron, something else has to gain it. Now, in the net equation, we only write what changed. So let's go back. What did not change in this reaction? The zinc changed, it lost 2 electrons. The hydrogen changed, it gained 2 electrons. Did the bromide ion change? The answer is no. It has a -1 oxidation number here and a -1 here. So it doesn't change. So you're not going to write the bromine in your net ionic equation because the oxidation number of that doesn't change. We're going to write our zinc solid, plus 2 H pluses, because remember this is aqueous, so it's actually dissolved. And when it's dissolved, these are split up. H plus, Br minus. That's aqueous. And that's going to form aqueous zinc, which has a +2 charge. Look up here. That's why I have to know my charges. That's aqueous, because the zinc, or is it aqueous? I think it's aqueous. Let's check our solubility rules. Yes, it's aqueous. If it wasn't, I don't think you would write the bromine anyway, but it is, so we don't have to worry about that right now. And our hydrogen changed on this side, so we have H2 gas over here. So this is our net ionic equation. We don't write the bromide ion here or here because its oxidation number doesn't change. Nothing's changing about the bromide. Net means you only write what changed. Oops, that was my sample. Now I have to do a whole nother problem. So I'm going to stop there. I was supposed to do aluminum in the sample problem, but I think we can work on that in class. So aluminum would be very similar, except instead of zinc here, you'd have aluminum solid. And then aluminum would get oxidized to a +3, not a +2. So we can talk about that in class. The end.